Hi, and welcome back to the Anatomy of Synergy. The purpose of this series is to demonstrate how to create and assemble the building blocks that comprise a Synergy application. In the last video, we used the Synergy decimal data type to store numeric data. We'll continue using numeric data in our discussion of the implied-decimal data type. Let's get started. The implied-decimal data type is very similar to the decimal data type. Like decimal data, implied-decimal data uses ASCII characters to store numbers. Each byte in an implied decimal value consists of a single digit. If the number is negative, the last byte is internally stored as the equivalent lowercase letter p through y. The difference between the two data types is that decimal data can only represent whole numbers, while implied decimal data includes an implied decimal point, so it can represent fractional values. In mathematical terms, the implied decimal type can store decimal numbers, while the decimal type, despite its name, can only store integers. Let's see how implied decimal data is defined. First, we'll make a new record. Just like a decimal field, you can define an implied decimal field with the letter D. But while the definition for a decimal only requires D and the size, an implied decimal also requires a decimal point and a precision value. As with all of the data types we've examined so far, the size value determines the total number of bytes that the field uses, which is also the maximum number of digits the field can handle. Implied decimal fields can have a size as small as 1 or as large as 28. The precision value in an implied decimal field defines the number of decimal places the field will use. The precision value can be as low as 0 or as high as the size of the field, up to a maximum of 28. Note that the size value is the total number of digits in the field, including digits before and after the decimal point, while the precision value is the number of digits to the right of the decimal point. For this reason, the precision value cannot be higher than the size value. Code like this will cause a compiler error. Let's see what an implied decimal field looks like at runtime. We have an implied decimal field with a total length of 10 digits and with 5 decimal places. Let's assign it a value. Now we'll run the program and see what it looks like. Before a value is assigned, the field has a default value of 0.0. Notice that the alpha representation of the field has 10 zeros, while the implied decimal representation shows a 0 with 5 decimal places. Now we'll assign the value. Notice that the alpha representation pads the number with leading and trailing zeros. Also notice that no decimal point is stored in the field. When the data is interpreted as a D10.5 field, the decimal point is placed correctly and the leading 0 is left off. Because the field was defined with 5 decimal places, a value from the field will always be represented with 5 decimal places, even if the input value has a different precision. Let's define a few more implied decimal fields and try some mathematical operations. Here we've defined 2 implied decimal fields. We've also added 2 blank alpha fields to separate the other fields. This will make it easier to tell the fields apart in the debugger. We won't access the alpha fields, so we don't have to give them names. Now let's add some code. In the previous video, we saw that the decimal field needed to be big enough to hold the result of an arithmetic operation. The same is true for implied decimals. The difference with implied decimals is that you also have to make sure the whole number portion of the field is big enough to hold the whole number portion of the result. IDES2 is 7 bytes long, so it would be big enough to hold the entire result, but its whole number portion is only 4 bytes long, which isn't long enough to hold the 5-byte whole number portion of the result. You also have to consider the fractional part of the implied decimal field. If a value is stored in a field that doesn't have enough decimal places, some precision will be lost. Here, the decimal portion was rounded from 0.66 to 0.7. If the result was stored in a field with more decimal places, the exact value would result. Because rounding is the default behavior, it would also occur if you assigned an implied decimal value to a decimal field. In that case, the result would be rounded to the nearest whole number, and all digits after the decimal point would be lost. You can change the default behavior by setting system option number 11. If this option is set, Synergy DBL truncates results at compile time. This concludes our introduction to Implied-Decimal Data. We've learned the basics of the Implied-Decimal Data type, how to define an implied decimal field, and how to use it in a Synergy program. We've seen how the runtime deals with precision in implied decimal data, and how to avoid some problems that could arise from using implied decimals. In our next video, we'll introduce you to the integer data type. Thanks for watching!